Welcome to ChemDoctor, and this video is going to be the first video in the series on chemical kinetics. All right, so what are chemical kinetics? Now, to understand this, you sort of have to think about chemical reactions in general, what controls them. And really, it boils down to two main things. There's chemical kinetics, which is how fast the reaction is going to occur, and there are the thermodynamics, which control how much product that we're going to produce after the reaction has reached equilibrium. And what the student needs to understand is that once we reach equilibrium, the reaction is essentially over from the point of view that you are in a place where now the forward rate of the reaction is equal to the reverse rate of the reaction. So the first thing out of the gate is to really try and get a qualitative understanding of what the difference is between studying the kinetics of a reaction versus the equilibrium position of the reaction. So the first thing that I want to do is draw your attention to the diagram on the left side of the screen. And here what we're doing is just simply following the time course of the chemical equation that I have listed at the top of the diagram. So we're following the reaction of iodine with hydrogen to produce hydrogen or hydroiodic acid. And what you can see here are two different curves. The hydrogen and the iodine decrease with time because these two reactants, well, that's what they are. They're reactants. And so as they collide and as they undergo this transformation into HI, the concentration of the I2 and the H2 decrease with time. And so you can see that basically in this reaction, I think I'm going to rewrite the equation here. In this reaction, we started with 1 molar of the I2 and 1 molar of the H2. And you can see from the progression of the reaction that over time the concentration of I2 and H2 are decreasing and approaching 0. All right, and as the concentrations of I2 and H2 decrease with time, you can see that the HI, which is now being produced as these two things react, is increasing with time and is approaching the 2 molar mark here. So this reaction, and the way that I'm depicting it here, goes to completion. So if you've already had equilibrium, and how this is taught at the university level or at the high school level, say in an AP course, is going to be different depending on the teacher or the professor. In my class, I do kinetics after equilibrium. So in that case, you've already had experience with the ICE tables. So what I could do is I could write, all right, here's before the reaction happens. This is the situation. After the reaction, in the way that I'm depicting this diagram here, the I2 and the H2 would be close to 0. So I'll put this little squiggly here meaning approximate, and the HI would be close to 2 molar, which is what you would expect for the stoichiometry if this reaction went to completion. All right, now to clarify what I'm talking about, all right, we can sort of do it this way. The study of chemical kinetics, as I've defined by definition here, studies the rates of chemical reactions, and I'm going to come back to this idea of rate in a minute. But we can boil this down to two words. If we're studying kinetics, what we're interested in is how fast. That's a way of thinking about it, all right? How fast is the reaction? On what kind of time scale is this happening? Is it a matter of seconds that we reach the equilibrium point? Or is it a matter of hours? Or is it a matter of days? How fast is the reaction going from time 0 to the point where we reach equilibrium, to the point where the forward rate is equal to the reverse rate of the reaction? And that's where both of these curves, if you look closely, have turned over flat. So in other words, up here in this region of the HI, there is now no net change in the concentration of that product. And if you look closely at the line that depicts the I2 and the H2, there's no net change of either of the reactants at this point. Neither the product or the reactants are truly, well, in the case of the reactants, they are not truly at zero. I only put it this way to indicate that they are approaching that point, because this reaction is the way it's depicted is going to near completion, and the HI in this case is not exactly 2 molar, but it is approaching that value. The major point being that at this time in the reaction, the products and the reactants have reached their equilibrium values. All right. So the kinetics is the study of how fast we reach that transformation, and the equilibrium, if you will, or really this boils down to the thermodynamics. Quite frankly, the thermodynamics of the reaction. This tells us how much. How much are we going to get? What's the ratio of the products to the reactants going to be? All right. Now, you can see when you look at my diagram here that I've basically, and this is sort of arbitrary, I've drawn a line here to indicate where we can sort of separate the kinetics of a reaction from the equilibrium. And that point is essentially where the reverse reaction is occurring now, to the extent where these lines start to lay over and go asymptotic to the maximal values that are expected in the reaction. So in this case, the H2 and the I2 are decreasing towards 0. The HI is increasing towards a value of 2 molar. And I've drawn this red line here to indicate sort of arbitrarily on here where you can see that the slope of these lines are pretty close to linear in these regions. So I'm going to add a red line here. So if we go from time 0 on the HI, you can see sort of that in this region here, the line is essentially linear the closer we get to 0. And in the case of the, I'll change the color here. In the case of the HI and the I2, if I draw a tangent, this portion of the line in this region is pretty well linear. So down here, as we approach 0, this is where the kinetics of the reaction are studied. This is where we study the rate of the reaction, how fast the reaction is happening. All right. Now, when we talk about a rate, what are we talking about? All right. The easiest thing for the viewer to think about maybe is driving in a car, and we talk about, all right, how many miles we've gone per hour of driving. This is a simple rate, distance divided by the time. All right. So for a chemical reaction, what are we going to measure for our rate? Well, in a chemical reaction, what we're going to do to measure the rate is we're going to measure the change in concentration. So in this case, I'm going to put it in terms of the hydrogen. All right. So the change in the concentration of H2 over the change in time. All right, same idea as distance per time. In this case, we're going to measure this as a change in molarity, a change in concentration. So let me put that in words. So it's going to be change in concentration. And usually this is going to be molarity. Although, quite frankly, in a kinetics lab, they're going to follow the rate based on something that's convenient. So it could be a change in partial pressure, for example, or a change in absorbance on a spectrophotometer. But the main thing is it's going to be a change in some quantity over a change in some time frame. All right? And the time frame could be seconds, it could be, it could be minutes, it could be hours, it could be nanoseconds. It's going to be this change, whatever the change in concentration versus change in time is. It's going to depend on what a set of convenient units are for that lab to actually measure the change. All right, now how do we get that from a graph? So I'm going to take this graph and I'm going to redraw it so that it's larger. All right, and I'm just going to freehand this thing. Now, I'm only going to draw the H2 here. And again, the graph for the H2, it's going to start up here at 1 molar. That concentration is what we call our initial concentration, all right? Initial concentration of the material. And over time, what we expect is for the rate of H2 as it's used to decrease. So it's going to go like this. And it's going to approach some value down here. Again, because this chemical reaction, the way it's depicted is going to completion, well, this value is going to be somewhere close to 0. But you need to remember that whatever value this thing approaches as we reach the equilibrium point where the rate of the forward reaction is equal to the rate of the reverse reaction, this point down here, whatever it is going to be determined by the equilibrium. And for a reactant, that point where that curve becomes asymptotic, where it flattens out, may not be 0. Or even close to 0. It's going to depend again on what the equilibrium point is. Now, let's get back to the kinetics. So I'm going to say right now that arbitrarily I'm going to draw a line down here, because this is where you can see this line is really starting to flatten out. So in this portion of our line, this is where the reverse reaction is starting to become prevalent, and that's why the line is flipping over. And when we get down in here, the forward rate and the reverse rate are equal. Now, how do we measure the rate? All right, so what we're going to do is we're going to pick 2 points on this line. All right, we'll say here's 1 point and here's the other. All right, and this point right here is going to have an x value and it's going to have a y value. The x value is going to be a time value that I'm just going to call t1. And the y value, all right, here, let's just draw the line over. So this is going to be my H2 at time 1, all right? And we draw this baby down here like that, and we're going to be at T1. And then our second point here, well, okay, let me put this in. So here's my H2 at time 1, all right? And then this point right here, and I'm going to move this out of the way here a little bit like that. All right, now getting back to it. All right, so this second point is going to have its own unique T2, all right, which is further into the experimental time frame, right? We're further into the experiment. And then our H2 value, our second H2 value will be here. It should be less than our initial value because the time frame of the reaction has increased, and that means that the H2 concentration should have gone down, and this value will be T2. All right, and then we're going to have our H2 concentration, which is now going to be at T2. Now, how do we find the rate? So the rate of the reaction, and in this case it's going to be an average rate, all right? So the rate of the reaction is going to be the rise over the run, right? So it's going to be H2 at T2 minus H2 at T1, all right? And this is going to be divided by T2 minus T1. And this is going to give us an average rate for the time interval that we have between these 2 points. So we can draw a tangent, and I'll get this as straight as I can. So we basically took a tangent to the curve, and the average rate that we found here, to be very clear about it, gives us the average rate for this interval in here, because this is where our tangent goes along the line. All right, now the average rate that we would have found here, if I actually put numbers into it, is the average rate of this interval. All right, the average rate of this interval. It's not the average rate, all right, not the average rate of this interval. So in other words, if we wanted to know the average rate of this interval, we would have to do a similar calculation with a set of new values. All right, so the average rate we found, all right, is not the average rate of any other interval on this line, only the interval that appears here. Now, to finish this video, the last thing I want to say is that we found the average rate of the H2, all right, and that average rate is proportional to the HI. So if we wanted to find the HI average rate of formation through this same interval, all right, we would have to multiply the average rate of HI that we found here by a factor of 2, because the HI is being formed at literally twice the rate of the H2 because of the stoichiometry of the reaction. All right, so remember, there was a 1 in front of the I2 and a 1 in front of the H2. The H2 is going to disappear at a rate which is going to be 1/2 of the rate at which the HI is formed because of the stoichiometry of the reaction. We'll come back to this idea in subsequent videos. So with that, I'm going to go ahead and close.